All right, so more here on molecular orbital theory for polyatomics. So I guess this is part two. We're going to go see some more examples of how we find our ligand group orbitals, how we start putting them together, symmetries, all that fun stuff, and now making that clear connection to all the wonderful symmetry stuff that we've done. Again, don't forget all the conditions that we have to fulfill for doing our molecular orbitals. We need to have symmetries and have the same sign for our wave function overlap. That gives us our linear combination. To form a linear combination, we must have energies that are similar, and we must be close in proximity. Again, we're not going to functionally worry about that in these small molecule examples that we're doing today. So in the last video, we went over an example of a bent molecule, and we had the ligand group orbital from the hydrogens for something like beryllium hydride. We said, oh, we've got a plus-plus, we've got a plus-minus combination here, so that was a relatively simple one to do. But as we start getting more and more complicated, it's going to not be quite as simple. So, for example, with the AX3 trigonal planar case, which is now D3H symmetry, how are we going to deal with now having 3s orbitals? How many combinations are we going to need? How many are going to be realistic to have? So remember, if we start with 3 atomic orbitals, we need 3 ligand group orbitals out of this. So how are we going to do that? What's our trick? I mean, I guess we could start playing plus minus games, but eventually we're going to run into some problems with that. So let's do this in a more structured way. How we're going to do this is by doing the same analysis we did to understand vibrations, but now doing it in regard to orbitals. So we want 3 orbitals to start with. We're going to get 3 ligand groups out of it. What we're going to do is the same process we did with our 3n degrees of freedom analysis. So, for example, I'm going to say, all right, I want to know my representation for these orbitals. I'm going to start with my orbitals that I have here. They're all positive in this case. And I'm going to say, what is the character that we would get under an E transformation of these orbitals? So when I look at them, I would say for E, well, that one stays in the same place and it does not change sign. This one stays in the same place, it does not change sign. This one stays in the same place, it does not change sign. So the character for my E symmetry element would be equal to 3. Boom. Now we can do the same analysis for C3. So if we do a C3 rotation, we're going to rotate these 3 orbitals. How many of them stay in the same place? None of them. So therefore, we get a 0 overall for this. Therefore, our character for C3 equals 0. Let's do one more example here. Let's look at one of our C2s. And to highlight that, the C2 is one here, one here, one here. Doesn't matter which one we do. We can look at any one we want. Just for simplicity's sake, let's use this one, okay? And we're going to do that C2 rotation here. So when we look at that, we say, well, what things move? This one moves, this one moves. So the only one we have to care about is that one at the top. Does it change sign or does it stay the same? It's still positive, so it gets a 1. So the character for C2 is going to be 1. Now, I'll tell you, you should probably be able to figure out these final 3, so definitely take a moment and see if you can do that. Looking at these s orbitals and say, how do they transform? What representation? What's the character that I'm going to get for each of those transformations? So just as a reminder, what we've done here is we have found the reducible representation. We want to know, how do we write our irreducible combination to get that reducible that we've just found? We want to do now the decomposition. And our decomposition is just like we've done before. So I didn't write the equation here, but you've got that in your notes. 1 over 12, where does that come from? 12 is the order. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, because we have 12 symmetry operations here. So that's where we get our group. And now we just have to do our decomposition analysis. So I have, for my symmetry element, I have the number of symmetry elements times the reducible representation character times the irreducible representation character here. Then I go on for C3. Now I'm looking at it. I've got how many symmetry operations do I have? I have 2. I have a 0 because that is my character here. And then finally, I have my character from the irreducible. And we just continually do that for all of our different groups. So if I look at A1, I find out that one of my ligand group orbitals has to have A1 prime symmetry. That's what our analysis does. Definitely take the time to work out the number of each of these representations. And I'll give you a hint, you don't have to do all of them because you know how many you have to have. You need 3 ligand group orbitals. So as I go through, I get 1 here for A1. I go on to A2 prime and I get 0. Down here for E prime, I get 1. So I've got 1 and 2. This is my 3 ligand group orbitals because, again, E levels are doubly degenerate, so they count for 2. So my reducible representation that I found up here in the previous step can be broken down into a single A prime 1 state and a doubly degenerate E prime state. So those are my orbitals that I'm going to have. From here, we can start building our MO diagram, and I would tell you things like that you would already know, like S orbitals are lower in energy than P orbitals. Cool. What you might not know is that the hydrogen 1s is similar in energy to the 2p orbital on, say, boron. This would be something I'd have to tell you so that you'd know how does your central atom relate to the 3 things around it. So this example might be BH3, might be a good one to think about here, hence why I use boron here. Then we'd have to ask the question of how do the p orbitals transform around that boron? Well, then we could go right back to our character table and say, all right, what are our p orbital symmetries? I look down here for x and y, they're E prime. Our z orbital transforms as A2 double prime. So our p orbitals are A2 double prime plus E prime. And just a reminder here again, we have this E prime state. It's degenerate, so there are 2 here, so don't forget about them. So we've got a total of 3 p orbitals, even though our representation only has 2 symmetry labels in it. All right, then we can start putting them together. So over here for boron, I said that, we've got our 2s level, which s orbitals on their own are always going to be totally symmetric. And we've got now the A double prime and the E prime state here. And we're going to make interactions with an E prime and A1 prime over here from our ligand group orbitals. So let's see how that works out. So if I look here, I've only got this singular A1, a singular A1. So I've got 2 A1s, therefore I have 2 molecular orbitals I have to generate. Here's one. Here's the other. Next one I'll look at, I've got my 2px and py transform with E prime symmetry. My ligand group orbital, we saw an E prime. So remember, E is doubly degenerate. There are 2 states there, so they're now on each side. I have a total of 2p plus 2 ligand group orbitals, which are the E prime. So that's a total of 4 MOs I'm generating. 1, 2, 3, 4. There we go. The last orbital I have up here is this 2pz, which had an A2 double prime. But notice we didn't have anything on the ligand group orbitals that matched up with that. So it just sits here alone. It is a non-bonding orbital. There we go. I've also shown here the description of what they would look like. This would be far past what we need to go to, but here is my ligand group orbitals, 1, 2, and 3, and the two that have E-symmetry are this one. This one down here is the one that has the A1 prime symmetry. You wouldn't be expected to figure that out, but I like to show it. Again, here's the geometric analysis over here. When we add them all up, we get all the wonderful shapes of it. Again, something else you would not have to do, but nice to know what it looks like. Now, that previous example was a D3H case, but recognize we could do a lot of the same stuff for a similar case. Instead of trigonal planar, we could do trigonal pyramidal, where we could have a C3V geometry. And let's do this in the case of AH3 again. So all we have to deal with is s orbitals all the way around. Same idea, and a possible example of something like this would be like ammonia. So now we've gone to something that's trigonal pyramidal. How are its orbitals going to be different? What do we have to do differently? Oh no, is this a whole new thing? Let's look at it. Essentially, we have to do the same process, but now instead of looking at the D3H, now we're looking at a C3V symmetry. So we have to do our same analysis, but now we have 3 different symmetry elements that we have to look at. So I'm going to look at my ligand group orbital. They're all positive s orbitals. I'm going to say what happens with an E transformation. Well, none of them move, so that's 3. They all stay the same sign, so that's 1. So our total character for E is going to be 3. If I look at the C3 rotation, none of them stay in the same spot, so therefore our character for C3 is going to be a 0. And now for a sigma V here, this doesn't matter really where you put it, but I could look at this axis. Only one s orbital stays in the same place. It stays the same sign, so therefore my character is going to be 1 for this sigma V. So that is now my reducible representation for this ligand group orbital. Now we just need to figure out, how does this decompose? How do we break this apart into its irreducible components? And again, here's the full decomposition analysis. I'm not going to spend a whole lot of time going through this. By now, you've probably seen enough examples of this, but definitely prove to yourself that yes, you get 1 here, 0, 1, which means that our reducible representation for our ligand group orbital is A1 plus E. So we now have our 3 ligand group orbitals because E is degenerate. If we wanted to look up while we're here, we could look up the p orbitals. So for example, for the nitrogen, we've got X and Y are an E, and our Z is an A1. So now we see some slightly different results than what we saw in the planar case, because now we have different orbital symmetries, different orbitals that can overlap. So let's take a look at them here. Let's just map them out real quick. Here I have an A1 state. Here I have another A1 state. Here's another one. So I have 3 orbitals that I'm bringing in. So therefore I have to have 3 molecular orbitals. I get 1, 2, and 3. On the ligand group side, we're now left with the E. Let's use a different color for that, so that's not so goofy. Let's use blue. Here's my 2 E states. Over here, they are the PX and the PY. So I have a total of 1, 2, 3, 4. 2, 4. There we go. Notice there are no non-bonding states that we have here. So that's different again. The ligand group orbitals look very similar. As we saw before, that shouldn't necessarily be surprising because they're still just talking about 3s orbitals that are in a triangular spacing. So nothing's really changed there. It's just the geometry that we're looking at about that central atom, which does make our final visualizations a little bit different here. Again, no, you're not going to have to figure out what these orbitals look like, so these pictures over here are not important in that regard. You're not going to have to draw them. You should be able to say, okay, if I give you the highest occupied molecular orbital having A1 symmetry, and I show you this, you should be able to use a character table to demonstrate that. Okay? Energetically, that's another piece of this that we'd have to be mindful of. No, I'm not going to ask you to put them in energy ordering. That's a PChem question. You need to be able to solve energies here, and we're not going to do that for this course. So just real quick, final comparison. We looked at BH3 versus NH3. Major symmetry difference here is we're looking at two different point groups. But the fun part is they use the exact same ligand group orbital set. It's not going to look any different, but since they are in different point groups, these orbitals will have different symmetries. And because of that, when we form our molecular orbitals here in the center, we see a different pattern of matching up between the two different sides because now we have different symmetries. So that's kind of the cool stuff here. And I guess I can point out that, hey, we're using hydrogens in these examples where you just have s orbitals. But what were to happen if we were to turn this into like BF3 and NAF3? Then we'd have an s orbital and a p orbital out there for our ligand group orbitals. How would we deal with that? Probably see that in one more video, and then we'll probably close out molecular orbitals. But just showing you how the process works and how we can use symmetry to better understand what molecular orbitals must look like. All right, that'll do it for this video then. So I'll be around as always. How can I answer your questions? What can I clarify? Let's talk about it. And until I see you next time, be excellent to each other.